So we're looking at how to draw a ray diagram for a convex mirror. Convex mirror means the shiny side is on the belly, as it were. So what we do is we've drawn the principal axis, but in a convex mirror, the focus and the center of curvature are behind, or on the opposite side to the shiny side. So the shiny side is over here. So we've drawn an arrow in front of the mirror, and we use the same technique as always. We draw two rays, one from the top of the object hitting the mirror and then reflecting back. But to locate how it reflects back, what we do is we extrapolate a line back to the focus. So use a straight edge, draw a dotted line. The ray isn't actually penetrating the mirror, but what it does is it gives you the line for the direction of the reflected ray. Then you draw a second ray that is pointed directly at the focus of the mirror. So it starts from the top of the object. It tries to get to the focus, but it hits the mirror before it reaches it, and then it reflects back parallel to the principal axis. Now you have your two reflected rays continuing that way. What you want to do is extrapolate them backwards, and where the two reflected rays touch, and I've done that in red here, where the two reflected rays intersect, that is where your image is going to appear. So we can see that with a convex mirror, the image is always going to be smaller, it's going to be upright, it's going to appear behind the reflective surface, and it's going to be virtual. You cannot project an image from a convex mirror because the rays diverge. You cannot project it onto the screen. You can only see the image, and it's a virtual image. Note well that when you use the magnification equation to calculate with the position of the object or the image, that the mirror and magnification equations are used. They can be used for concave mirrors, for convex mirrors as well as concave mirrors. However, since the focal point is behind the mirror, you see the focal point here is behind the mirror, the focal length for a convex mirror is written in as negative. So this distance, whatever it measures, when you enter it into the equation, it's a negative focal length. And we have an example here in a practical problem. It says a convex surveillance mirror in a convenience store has a focal length of 0.4 meters. A customer who is 1.7 meters tall is standing 4.5 meters in front of the mirror. A, calculate the image distance, B, the image height. So we're going to use the mirror equation. 1 over f is equal to 1 over the distance of the image plus 1 over the distance of the object. We enter the focal length as negative 0.4. And just be careful when you enter your numbers. Remember, first of all, that if you have a convex mirror, the focal length is going to be a negative number. And secondly, if your units are in meters, then stay in meters. You can also enter all your units in centimeters, but whatever you do, don't put a mix of meters and centimeters. All your units have to be consistent, or else you get a wrong answer. So we did everything in meters here. 1 over negative 0.4 is equal to 1 over di, the thing that we're trying to find, plus 1 over distance of the object, which is 4.5 meters. We then, what we did is we transposed the di to isolate it. We brought the f to this side, so it becomes from 1 over negative 0.4 to 1 over positive 0.4. Find a common denominator of 180. We multiply both top and bottom by the numbers necessary to get the correct numerators, and totals up to 490 over 180. Now, given that 1 over di is a negative number, we then transfer the negative number to the other side, and then we flip both fractions to find out what di is. And that gives us di over 1 is equal to negative 18 over 49. Using our calculators, we found that that equals 0.367. So that tells us that the distance of the image is behind the mirror, and that it is 0.367 meters. We then are asked in the second part of the question to find the image height. And we use the magnification equation for that. The magnification is equal to hi over ho, which is also equal to negative di over do. We're not actually using the magnification part of the equation, so we've only used these two parts. We've isolated for hi by transposing the ho, height of the object. We enter our numbers, and remember again, the distance of the image is negative 0.367, but the formula also has a negative sign, so it's a double negative, which turns it into a positive. The answer is 0.1386. So the height of the image is 0.1386 meters. it's significantly less than the height of the object, which is 1.7. And that's consistent with what convex mirrors do. They make the image look smaller. They create an image which is smaller than the actual object.